Good evening, everyone, and welcome to SURF's Nobel Day event. My name is Constance Walter. I'm the Communications Director for the Sanford Underground Research Facility, and I'm going to be your host tonight. Now, Nobel Day is a very special event at SURF, and tonight we celebrate scientific achievement, and we will also be giving out the CORS Award. So this event is sponsored by the Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, and Jolene and Chuck Lichtenwallner. We thank them for their generous gifts and their continuing support of science, outreach, and education in the Black Hills. Since 2015, Crow Peak has been a part of our Deep Talks events, and we are grateful for their ongoing support. Incidentally, Crow Peak was also a CORS Award winner. They were the first, in fact, in 2018. So that we're always really grateful that they have been a part of this for so long. Crow Peak is also sponsoring tonight's door prizes, which include a growler with one fill, a 6-pack of Crow Peak's locally brewed craft beer, and a gift certificate with a Crow Peak t-shirt. Now, the poll you see on your screen is only available to our Zoom webinar viewers. So if you're watching on Facebook, join us next time on Zoom for a chance to win. To enter to win this prize, you must be 21 years of age or older, and you must be able to pick up the door prize at Crow Peak in Spearfish, South Dakota. If you are joining us via Zoom webinar, please select the option to enter yourself. We will randomly select a winner at the end of the event and contact our winners via email. We also want to give away some SURF swag tonight. And we're really excited about this because this just came in the mail today. And if you participate in the polls throughout the event on Zoom and Facebook, you'll be entered to win. The more polls you answer, the better your chances of winning this cool SURF beanie. Thanks, Aaron and Adam, for your wonderful modeling. Tonight, as always, we would love to hear your questions. If you're joining us through Zoom, please use the Q&A function to submit questions. If you're watching live on Facebook, add your questions to the comments section. So the Communication and Outreach Experiences in Science, or CORS Award, is given annually to an individual, group, business, or organization that supports public STEM education and outreach within the region. The recipient is selected by a committee that takes into consideration ongoing support of science education, whether through sponsorships or service, a passion for science education, and a visible commitment to public science outreach in the region. Since 1997, visitors to the Journey Museum and Learning Center in Rapid City have explored the Black Hills area through the lenses of history, science, and culture. This year, we are proud to recognize them with the CORS Award, which is in honor of their dedication to public outreach in the sciences. Recipients of the award receive a commemorative engraved core and a certificate. At this time, we're going to share a short video that introduces you to the Journey Museum and some of the work they do. Now, please join me in welcoming Troy Kilpatrick, Director of the Journey Museum, who is accepting the award on behalf of the museum and its staff. Hello, Troy. Thank you so much. We have some wonderful gifts for you tonight. First of all, I'm going to show this to our audience. This is the core that is given to the CORES Award recipient. And that is you can use that for just about anything, Troy. Additionally, we have this lovely certificate for you to hang up in somewhere in a prominent position at the Journey Museum, we hope. And so there you go. And I'm going to give Troy a few minutes to tell us a little bit about the Journey Museum and why he's so excited about being here tonight.
Thank you, Connie. Well, first of all, thank you all. Thanks everybody here at Sanford Underground Research Facility and everybody who's been involved in recognizing the Journey Museum. It's an extraordinarily grateful feeling to be here tonight and to be recognized, our team being recognized for everything we've done. We've all been on a really special experience of our lives here, 2020 and 2021. We persevered by a lot of ingenuity within the education team. And this award really means a lot to our organization because of all of that. Education is such an important thing. And so I'm very grateful. And I want to make sure, though, that this award isn't about Troy. It's about the educators that we've had on our team, past and present, the volunteers, our education committee, our board of directors at the Museum Alliance of Rapid City, our partners, and ultimately all of our community members who are supporting us at the Journey so that we can make sure that the journey continues. So thank you all here again for this wonderful award. What a perfect time for us to have it. And Connie, I'm going to let you take the show back over.
Again, Troy, congratulations to you and your team. This is a well-deserved award, and we're so grateful that we were able to do this and to have you here in person to do that with us. So tonight we have a really special speaker. He's our science director at SURF, and he is here tonight to discuss the work of Dr. Raymond Davis. Davis, as most of you know, was a nuclear chemist from Brookhaven National Laboratory, who for nearly 3 decades operated a solar neutrino experiment on the 4850 level of the Homestake gold mine. Dr. Heise's early research was strongly connected to Davis. Heise worked at SNOLAB with Nobel laureate Dr. Arthur B. MacDonald, who shared the 2015 Nobel Prize in Physics with Dr., and I hope I say this right, Takaki Kajita. Together, the two of them solved a long-standing puzzle in particle physics that had been created, actually, by Davis's work. Why were there only 1/3 as many neutrinos as had been predicted by Dr. John Bacall? Their discovery that neutrinos changed types or flavors as they traveled over long distances earned Davis a share of the Nobel Prize in 2002. Dr. Heise is an accomplished researcher in his own right. In addition to his work at SNOLAB, where he held a position as the detector manager, Heise has held a postdoctoral position at Los Alamos National Laboratory and has been involved in the development of several scientific publications. He graduated with a PhD in neutrino physics from the University of British Columbia, Canada, and has worked in underground science for 25+ years, 13 of which have been at SURF. Tonight, Dr. Heise will revisit SURF's scientific roots and the legacy of transformational research with Dr. Ray Davis's neutrino experiment. Again, I want to remind our guests to take part in the polls and submit questions. And at this time, I would like to welcome Dr. Heise.
And share here. Two seconds. Let's try again. Share screen. How's that look? Very good. All right. Well, thank you, Constance. It's truly an honor to be discussing Ray Davis and his experimental work with everyone this evening. It's a great story. His pioneering work and legacy is why I'm here. It's why SURF is here. And I'm going to do my darndest to try to give justice, a just description to what Ray Davis did to bring us all here. I'm going to begin by saying that I'm not necessarily an expert in Ray Davis's chlorine experiment work, but I know some experts. And I want to start by thanking Bruce Cleveland and Ken Londe for their input. And with that introduction, let's dive in. All right. So I usually like to start my presentations by talking about big questions, looking how we like to look at the universe to find out what it's made of, how it works, like some of the experiments here at SURF are doing. And that's a part of tonight's story as well, but there's an important theme that I want to emphasize, and that's how seemingly little questions and painstakingly careful science can lead us to these big questions. So shown here is a timeline illustrating a brief history of neutrinos, starting from the invention of the neutrino by Pauli in 1930, leading to the initial discovery by Reines and Cowan in the late 1950s. And as a quick aside, Ray Davis also spent some time at the Savannah River reactors. And so some of his tests with the chlorine process that I'll get into in just a second were taking place right around the same time, right in the mid 1950s. And so in a manner of speaking, you could say that Ray was in the room where it happened, along with Reines and Cowan and their Nobel Prize winning work. The timeline includes some more recent activities and successes, as noted by Constance earlier. I was a part of the SNOW experiment that received the Nobel Prize in 2015. And notice that there's a placeholder at the bottom of this list for exciting new projects at SURF that may tell us something more about neutrinos and figure on this timeline of Nobel Prizes. I also want to point out that while many of us are familiar with neutrinos, given that we're sort of at this end of the time frame, what we'll be talking about this evening is mostly these early days when the neutrino was not a household term that you may recognize as from today. So in Davis's own words, he was hooked on neutrinos from the beginning. His academic career started right around the time that the neutrino was born in the early 1930s. And as we've already heard, exciting developments with neutrinos weaved in and out of Ray's life. His academic career then led to a position at Brookhaven National Lab, where he obviously had a great boss who said on his first day, when Ray showed up in his office to ask him what he should do, his boss said, "Go find something interesting to work on." So Ray went to the library, took out a paper by Crane, and there's an interesting quote here that I want to point out. The Crane paper acknowledges that not everyone would be willing to say that he believes in the existence of neutrinos. And this gets back to the statement I just made a moment ago about that neutrino not being a household term. Neutrino physics and even the existence of a neutrino hadn't been established yet, and so it was still very speculative. At Brookhaven, Davis went on to read articles that would eventually become his bread and butter. The chlorine-argon technique that was proposed by Pontecorvo and Alvarez is listed here. Chlorine interacting with a neutrino, in this case an electron neutrino, but they wouldn't have known that at the time, to produce argon and an electron. The argon then decays with a half-life of just around a month. Another thing that Ray found during his initial years at Brookhaven was captured here by Alvarez in this quote about the importance of understanding the background. And Ray really took that to heart, as we'll see in our journey through Ray's experiences. The picture here at the bottom right just shows the first page from Davis's lab book at Brookhaven. So he got right on it, finding something interesting to work on. So that background leads us into a discussion here about why we ended up going underground eventually. But in his early experiments, Ray explored some of the backgrounds both at the top of a mountain as well as in some shallow sites. So as you can see in the depiction, our planet is constantly bombarded by cosmic rays produced outside of our solar system. They interact with the upper atmosphere, atoms in the upper atmosphere, to produce muons, and those muons constitute a background. So on the surface, you hold out your hand, 2 or 3 are going through every second. If you go underground about a mile, as shown in the animation, you reduce that by roughly a factor of 10 million. So that 2 or 3 per second on the surface translates into 1 per month when you're underground at that depth. Ray was one of the first pioneers to leverage that advantage. Here's a quick summary of some of those early experiments that I just mentioned. So Ray hauled 50 gallons of his chlorine mixture up to the high altitude lab in Denver. He did some measurements and quantified some of the backgrounds that you would get from cosmic rays interacting, producing protons that then interact with the chlorine in his detector to produce the argon. That would also be a signal that would contaminate or cloud the neutrino experiments that he would go on to do. He got off the mountain, went down to sea level at Brookhaven. He did some tests at some research reactors there and still found no anti-neutrino induced events above the background. He even buried the tank 20 feet underground, knowing that this background was contributing. And he used that to set an upper limit on the solar neutrino flux. That, as I note here, wasn't the most sensitive measurement in the world, and it ended up being 15,000 times higher than the result that he would eventually get. And to put a fine point on that, a reviewer of this first paper had the following insightful review comment. One would not write a scientific paper describing an experiment for which the experiment stood on a mountaintop, reached for the moon, and concluded that the moon was more than 8 feet away from the top of the mountain. Ouch, that's a little bit of a harsh statement to take. But Ray was undaunted, and in fact, as we've already mentioned, he was hooked. Going underground, more than 20 feet this time, Ray's next stop was the Barberton mine in Ohio. So there he used roughly 1,000 gallons of a new chlorine mixture. This mine was operated by the Pittsburgh Plate Glass Company. They had a limestone mine that was about half the depth of the 4850 foot level that we're familiar here with that surf. The perchloroethylene, or dry cleaning fluid, this new chlorine mixture, was safer than his original chlorine carbon tetrachloride mixture. And so you can see we're already thinking about underground safety. It's a good thing. He refined his experimental technique to detect single argon atoms. And we're not going to get into too many details here, but I just want to call out some of the elements. First, he uses helium gas to remove the argon from his chlorine tanks. He then uses a cooled charcoal trap to remove the argon from the helium, usually cooled using liquid nitrogen. We're very familiar with liquid nitrogen here at SURF. And then finally, he needed a way to characterize the extraction efficiency. And for that purpose, he injected argon-36, a specific isotope that he could then trace after the fact. And that was different than argon-37, with the assumption that the two efficiencies were very similar. Picture on the bottom there just shows the setup at that Barberton mine. Ray and colleague with a fairly small experimental setup, a couple tanks, some helium gas, a gas handling system, a couple chairs, a couple tables, and he's good to go. We're going to take a quick side trip from experiment and just talk about the fact that at the same time, theory was being developed that would come to Ray Davis's aid as he was proposing his large-scale neutrino experiment. The graphic here shows a number of different reactions that occur to produce energy inside our star. These are the solar fusion reactions. Very few of these were known at the time of Ray Davis's introduction into neutrino physics. The first PP reactions here were known, but this reaction occurs at a low energy that wouldn't be available to Ray with his chlorine-argon method. As you can see there, it was about half too low for him to make use of that. But right around this time, there were additional neutrino reactions in the sun at a higher energy that were discovered. John Bacall was one of those theorists at the time, and in particular, some of the new high-energy beryllium-7 and boron-8 channels presented a great opportunity. You can see some big increases there, 1,000 times what was previously believed for the beryllium and 20 times higher for the boron. At the same time, Bacall also updated some of the theoretical predictions for the probabilities for interaction with the chlorine, which of course is instrumental for Ray Davis's work. The other thing I'll point out here before leaving this slide, despite all of the different channels, there's several different flavors, or sorry, that's a bad word actually, not flavors, one flavor, several different channels that produce neutrinos, but it's only the electron neutrino that are produced in any of these channels. Looking at this in another way, we can see the neutrino flux, so the number of neutrinos produced in the sun, as a function of that energy, and I've highlighted here the energy region and the types of neutrinos from those different channels occurring inside the sun that would be accessible by Ray Davis's chlorine-argon technique. And you can see if we were just looking at those PP neutrinos, the most abundant neutrinos, but at lower energy, Ray's technique wouldn't have been sensitive to that. And so we're going to stop here to do our first poll question. And what is that question? You need me to read it? Oh, yeah. No, well, I can sit here. Who designed the theory behind Ray Davis's work? And there's 4 choices there: John Bacall, Einstein, Vera Rubin, or Art McDonald. I'll give people a few seconds to.
Couple seconds, 80%.
Okay, very good. So most people picked up on John Bacall. I'd mentioned him briefly, and he's going to figure prominently in some of the next things we're going to talk about. So congratulations, good job everyone on that. And, oops, do I need to close the poll here? Nope, very good. Excellent, alrighty. So progress on both theory and experiment were captured in companion submissions to one of the most prestigious journals in physics called the Physical Review Letters, PRL for short. So the top one here was submitted by John Bacall regarding the theory of solar neutrinos, and the bottom one by Ray Davis talking about experimental techniques that could investigate those solar neutrino channels. And so this was a very powerful duo, I should say. And I should also maybe follow that up by saying not every duo is destined to propose solar neutrino experiments, unfortunately. Moving on, already. So with those ingredients in place, we were able to set some parameters for what this large-scale solar neutrino experiment will look like. So how big is it going to be? Well, based on the latest theory, they realized they needed about 100,000 gallons of this chlorine mixture. That size, that 100,000 gallons, sets the size of the tank, roughly 30 feet in diameter by 30 feet tall, which in turn sets the dimensions for the cavern that would need to host such an experiment, because it would have to be underground. We've already talked about the cosmic ray backgrounds that Ray appreciated, and he was able to do, based on a couple data points from earlier in his career, figure out where and how deep he wanted to go. So here's a plot from one of Ray's papers talking about where they expect the solar neutrinos to show up, and then the depth that you would need to get to have a good signal to noise ratio to be able to definitively detect those neutrinos. And so he realized, and you can read it from this plot, if you're expecting a signal here and you want, say, 30 or to 50 times a buffer here, then you're looking at a depth of around 4,000 meters water equivalent, or about 4,500 feet with standard rock. That presented both the size and depth requirements. The next stage is to go and figure out where we should, what mine we should try to convince to make such a cavern for the benefit of physics. Three options came to mind, and I list them here. There's the Anaconda copper mine in Butte, Montana. Turned out that was too small. They were proposing to do a borehole of a dimension that wasn't going to really be sufficient for this 100,000 gallons of dry cleaning fluid. The Homestake mine was also approached, as you might have guessed by this point, Meade, South Dakota, as many of us are aware. But the initial estimate from Homestake was too expensive. And so the last choice here, the Sunshine Mine in Idaho, was the Goldilocks of the three choices. It was the right size and came in under budget. And so I've been leading you astray. We're not going to Homestake, we're going to Sunshine. That's not true, of course. Turns out that plans to host the first large neutrino experiment at Sunshine fell apart. And a few years later, in 1972, there was a disaster at the Sunshine Mine. And I know when I came here, many of the miners and mining community knew about this. Almost 100 people died in this incident. And it makes you wonder, if the Davis chlorine experiment had gone to the Sunshine Mine, what would have happened to the field of neutrino physics? Luckily, we won't have to ponder that question too much, because we're going to Homestake. So it's still Sunshine or bust. And there's a nice quote here from Davis Bacall saying that they were very pleased with Homestake's plans and their cooperative attitude, which I'm not surprised in the least. And we're still on our way to Sunshine. And I put here one of the stickers that our very own Robin Barland helped design, and it really matches this beautifully already. We're gonna, so we're on our way to the 4850 foot level. Where on the 4850 foot level should this wonderful physics cavern be located? Just a few words on this level itself, a few points of interest. You go underground. Here you see about 10 miles or 16 kilometers of tunnels, very extensive. You can also, let me tell you a little bit about some of the labeling here. A couple shafts, there's the Yates shaft, the Ross shaft, 6 winds, which is an underground shaft, 3 winds, 4 winds, 5 shaft. The areas here labeled in green, read those as yellow, read those as gold. That's where the gold was mined. So 17 ledge, 11 ledge, 9 ledge, main ledge, those are all mining areas. And so this is where we're going to stop and ask the second poll question. And the question here is, Davis's experiment is closest to which Homestake shaft? And your choices are 5 shaft, 3 winds, the Ross shaft, or the Yates shaft. Give you a few seconds on that one. Couple more seconds. All righty. Okay. All right. The correct answer there, most of you got those. The right answer, it was the Yates shaft. And have that go away here. Close. There we go. There we go. So here's a zoom in close to the Yates shaft. You can see where the Davis cavern is located. A couple things you might not fully appreciate. Those of you who know this area, however, will see that there's a couple things that are a little odd. There's no connecting drift for where we currently have the Majorana demonstrator and the Black Hills State University underground campus low background counters. That lab area hasn't been developed. That was developed later on once SURF took over operation of the facility. Also, just as a point of interest on this particular level map, the ventilation drift, or what is now referred to as the west drift, didn't exist. That wasn't developed until the 1970s. We have a campus called the Ross campus near the Ross shaft. Those areas, those caverns, weren't excavated until the 80s. And so the level, the 48, 50-foot level, looked very different in Ray Davis's time compared to what we see today. And the other thing I want to point out, and the reason that Ray Davis's experiment is here and not next to all the shiny gold, is because if you're a parasitic physics experiment, you do not want to be between a mining company and what the mining company is mining, because that is not a good recipe for having your issues, your concerns addressed. It's you just being in the way of the bottom line for the company. And so this area here, for that reason, was chosen. And not to mention the rock in that particular area, the Yates amphibolite, is fantastic rock for making large caverns. All right. So with the site picked out, the Homestake miners went to work, developing a site for what, as you can see, was an atomic age experiment. You can just hear the announcer's voice. This is from the Sharp Bits. This was the Homestake Mining Company's internal newsletter from September 1965. And you can see a couple of the miners there working with a jackleg drill to develop in the decline leading down to the bottom of what would soon become Ray Davis's cavern. All right. So to give you a bit of a lay of the land, here's a schematic of Ray Davis's laboratory. So just a couple things to point out here. Of course, we have the main chlorine tank in the main cavern for the experiment. You can see a control room and a gas handling facility. We'll show you a picture of that here in just a second. There's a tanker car or a rail car used for delivering liquid nitrogen. Remember, Ray had to cool some of his apparatus. And so this looks very similar to what we currently do supplying the LZ experiment with liquid nitrogen. We pull it up on rails right to the same location. Here's the ramp where we saw the picture of the Homestake miner working with his jackleg drill. At the bottom there, we have some pumps for moving the perchloroethylene, circulating it through the tank. At the top of this decline, a couple interesting things. The very first dark matter experiment called IJEX was located on a little shelf in this cutout. This was not intended to be used for an experiment. It was used to support the mining activities for excavating the cavern. But every little bit of space underground is valuable. And that dark matter experiment found a home in the 1980s to start looking for dark matter as one of the very first experiments. More recently, this is where order $50 million worth of xenon used by the LZ experiment was stored before being transferred inside the titanium cryostat to look for dark matter. Speaking of dark matter. All right, let's go through some pictures here. Some of these are pretty cool black and white photos. So at the bottom of the decline was this really cool submarine door, and you can see a fairly substantial wall bulkhead. I think it was almost like a foot thick. This was because of the fact that they were, so the cavern with the chlorine tank was at the end of the construction filled with water to act as a shield against neutrons. And so it needed to be watertight. And so you can see some of the Homestake miners here installing that bulkhead and working on the door. If you happen to know where that door is, let us know. We'd be interested in seeing it again. The second picture here on the right-hand side just shows Ray Davis after the concrete floor was poured for the cavern, looking up at the expanse of his laboratory. You can see a monorail beam installed on the ceiling. Reading the article and short bits about this picture, they were really pointing out how well lit this was. Apparently most areas underground where miners work are not well lit. And you can also see some of the geology in this picture. That tank came down in pieces, as you might expect. The elevator or the cage was not big enough for something on the order of 40 feet long and 20 feet in diameter. And so you can take a look at the Yates cage at the time and see how those steel panels fit into the cage, and then how they were transported through the tunnels from the shaft station into the cavern. Not a lot of extra room there. Those tunnels are fairly small. All right, you can see the tank being fabricated, welders underground putting together those panels and ribs and pieces. There's a picture of Ray standing inside the partially completed tank, and this gives you a nice scale. So once again, the tank is 20 feet in diameter, 48 feet long. Pulling the walls together, making sure that it's nice and round. I like this picture for a couple of different reasons. First of all, you see a tank has been completed. There's a port. They've hooked up a vacuum pump and a leak checker. This is a tried and true experimental tradition of leak checking your vessels, and Ray Davis did the same. The other thing you might notice, besides the fact that they're not wearing safety glasses or anything like that, is this miner here is. I've seen him in lots of different pictures. I think he's smoking in every single one of them. He's got a nice cigar going there. And then finally, Ray and theory collaborator John McCall are underground once the tank is complete and leak tested, and they're ready to start taking some data. Speaking of taking data, here's data taking for the atomic age, as we learned earlier. You can see the homestake miners working with some of the, Ray's collaborators moving in a panel. This is the control room just outside of the main cavern. And they're measuring temperatures and pressures, much like many of the experiments that SURF currently do. And in fact, here is a picture of the LZ control room. Looks a little different. In fact, I think this control room is even more impressive, right? A whole wall. I think that's pretty cool. So that was the atomic age. This is beyond the atomic age. And we may have lost something a little bit in the translation there. But. So here's an interesting timeline showing the evolution of the Ray Davis experiment, really. Showing the evolution of theory and experiment sensitivity over the years, starting in the early 1940s, through the 1950s, all the way up to 1970. And so early on, you can see the experiment in this line up at the top and how it compares to theory. And this gap between experiment and theory means that Ray's experiment was not sensitive enough to test the theory of the time. And you can see around 1950, Ray's numbers are even off the scale. Recall that one reviewer basically saying, why waste my time with a measurement that isn't sensitive to do pretty much anything? And Ray recognized that, but he worked very hard, he and his theory collaborators, to bring these two curves much closer together. And we've talked about some of these milestones in our journey this evening. Ray's tests at the Ohio mine, John McCall and others developing and refining the solar energy flow and energy production in the sun, and how eventually theory and experiment meet around 1968, where Ray's experiment, his chlorine-argon technique, is sensitive enough to see neutrinos coming from the sun. So Ray and his collaborators did painstakingly careful science over decades. And you can see the result of that shown in this blue band. And what that represents, if you look on the y-axis here, that represents, or just imagine what that represents. It is measuring one argon atom every 2 days in 100,000 gallons of dry cleaning fluid for 25 years. That's one atom. He's looking for one atom every 2 days in 10 to the 31 atoms in his large solar neutrino detector. That's a hard way to make a living. That's very, very hard science. And you can easily see that the discrepancy between theory and experiment, that shows you on this plot here with the two bands, the blue band for Ray's experiment, and then the theory, how they are not in agreement. So Ray's band here, you can see his result about 2.5 in units that aren't important for our conversation this evening. So 2.5 compared to 6. Even for large values of 2.5, that doesn't equal 6. And by that, I mean the errors don't allow those two to overlap by a significant margin. So a suite of new experiments came online in the late 1980s and early 1990s, and they're shown here as well. Kamiokande in Japan using a water Cherenkov technique. Also in Italy, the GALEX experiment, and in the former Soviet Union, SAGE used gallium to also study solar neutrinos, using slightly different techniques. And they all saw less than theory predicted. As you can see here, the gray represents theory and the white represents the different experiments. And they're all much less than the theory would predict, including Ray's experiments. Before we leave this slide, though, it's important to revisit an observation that we made earlier, and that the sun only produces electron neutrinos, and Ray's experiment, as well as all of these experiments, are only sensitive to electron neutrinos. SNO experiment results came in 2001, and you can see that they validated both Ray Davis's experiment with roughly 1/3 of the neutrinos, in this case, the electron neutrinos, as well as theory. And so when you measure all of the types of neutrinos, as the SNO experiment was designed to do, you match the theory very well. SNO also had a channel that was only sensitive to the reaction that the other experiments were sensitive to, and it was able to then show, as I mentioned, both theory and previous experiments were correct. They were just looking at different things. And speaking of the SNO experiment, here's a sketch on the left-hand side. What you're looking at here is an experiment that used 1,000 tons of heavy water inside a central 40-foot diameter sphere surrounded by an array of almost 10,000 light sensors. This is almost 60 feet in diameter, all 6,800 feet underground in a nickel mine in Canada. And so shortly after the SNO result, Ray Davis was awarded the Nobel Prize in Physics in 2002. And so this slide here commemorates what looked like at the time a fairly humble beginning, his boss telling him to go find something interesting to work on, all of the hard work to get to homestake, to build his large neutrino experiment, was rewarded by the share of the Nobel Prize in 2002. There's a legacy that continues on beyond that, of course, and that Ray's work was instrumental, and it made it appropriate for us to then dedicate our first major physics laboratory underground as the Davis campus. And that was dedicated in 2012. Ray's widow, Anna Davis, is shown here with his Nobel Prize, standing in front of a new water shield, or a new tank. In this case, it was going to hold water for a series of dark matter experiments. So a little different than Ray's tank, but similarities nonetheless. And that tank lives on. And so the ring from Ray Davis's chlorine tank the entire tank was removed from the underground as we developed the Davis campus. That ring is now prominently and proudly displayed outside of the Sanford Lab Homestake Visitor Center, just down the hill from the lab. And you can see some pictures there. One on the left has the rainbow. It's hard to see perhaps, but there's an old mining shaft, one of the B&M shafts, seen through the ring. And then our communications team member enjoying the view from the ring. Another piece of news to pass on related to Ray Davis is the fact that SURF was designated as an APS, an American Physical Society, historical site. That announcement was made this past summer, or actually a year ago summer, September 2020. And with the pandemic, we're looking for a date for the dedication, possibly in the new year. But recognizing that this site is very significant for the history of physics, as I just talked through. And so finally, a quick bye from Ray here as he's swimming in his neutron shield, the water filling the cavern around his chlorine tank. And then finally, a picture here of the Davis campus and our food preparation area, Ray's Cafe. And with that, I will wrap it up. Thanks.
Okay, Jaret, thank you so much. That was fantastic. We have a few questions for you.
Mm-hmm.
One of the first is from Dr. Jose Alonso, our good friend.
Hey, Jose.
And he asks us, how did Homestake get from too expensive to being the chosen site?
That's a good question. I don't know all the ins and outs. I think, and I'm not sure if management changed or if there was any change there, but they did revise the estimate when Ray and John together came back and asked after the Sunshine deal fell through. I get the sense that Homestake and Homestake management viewed it differently than they did initially, and how exactly they viewed it differently, I'm not sure. But as you saw from the quote, Homestake was very cooperative. They featured the development of the cavern and the experiment in several of their internal Sharp Bits newsletters. So they were very excited. And as with many of these underground labs, it's sort of hard to picture those discussions where you're trying to convince a mining company to remove rock that has absolutely no chance of having any commercially sellable ore, whether it's gold, nickel, like at Snow Lab, or some of the other labs that have been developed around the world. It takes a company with vision, and I guess they found their vision, whether it took a couple tries or just those 2 tries, but we're really thankful that they did.
Thank you. Another question is, how many experiments are studying neutrinos today at SURF?
At SURF, let's see. So LBNF Dune is our major flagship experiment. They're not online yet. They are developing the laboratory currently. Majorana Demonstrator is studying neutrinos, looking for neutrinos double beta decay, testing their technologies and the purification techniques, the material fabrication techniques that are going to be used for a scaled up version of that experiment. So they are looking for neutrinos. Those are the main ones. We have others looking at dark matter, and I think Majorana would be the main neutrino experiment currently.
So can you give us an estimate on how many neutrino experiments there are around the world?
Oh boy, more than several. Let's see, I would say a couple dozen. That's roughly the number of dark matter experiments as well. And I think the last time I checked, those numbers were very similar. So I'd say a couple dozen.
Okay, and we also have another question. How did Ray Davis measure the argon?
So he had, we walked through that a little bit. He had the helium to get the argon out, and then he had the charcoal traps to separate the argon from the helium. From there, he had proportional counters, and so he put it into another sensitive device where the argon would decay and he would look for those decays. And we didn't touch on it in this evening's presentation very much, but the sensitivity of those proportional counters also evolved over time to make his measurements ever more sensitive.
Now I've got another question here that is asking how or what will Dune tell us about neutrinos when it does go online?
Very good question. Dune is a project that is exploring properties of neutrinos. Dune will inform the mass of the neutrinos, and in particular the hierarchy, which of the flavors of neutrinos, the electron, the muon, or the tau, is heavier or lighter. We still don't know that. We have some nominal, maybe biased assumptions on how that will work, but we want to verify that experimentally. But one of the main things will be looking for CP violation, looking for whether there's an ingredient in neutrino interactions, this CP phase, this property of neutrinos that allows it to slightly prefer matter over antimatter. We talked a little bit about why we're here, and of course it's Ray Davis and the legacy he lives. Why we're here writ large, why do we see a universe filled with matter and not light, is the question that Dune is hoping to answer. After the Big Bang, we expect that there were equal parts matter and antimatter formed. And if you remember your Star Trek physics, when matter and antimatter get close to another, they annihilate, they produce light, they produce energy. And that is not the universe we see. We see tables, chairs, stars, planets, galaxies. Those are all made of matter and not antimatter, but also not light. And we believe that the neutrino, it's already interesting in a whole bunch of different ways, but we believe the neutrino may have that property that allows neutrino interactions to choose matter slightly more than matter.
Is it possible that neutrinos could also be dark matter?
That's a very good question as well. And early on, that was a theory. That was what people were thinking until we measured the mass of the neutrino. We still haven't measured the mass, but we've measured it. We've found limits to know that the neutrinos, as we understand them today, are not heavy enough to constitute the dark matter. But early on, like I said, we didn't know that. The neutrino is the most abundant matter particle in the universe. So more than quarks and electrons and protons and neutrons and all that. Photons, particles of light, if you want to think of them as particles, but light is more abundant. But in terms of matter, it's the neutrino. There's more neutrinos than anything else. And even if they had a small amount of mass, the thought was that they could be dark matter, but we now know that they do not possess enough mass.
And I think this is going to be our last question. What are the big questions in neutrino science today? You've touched on some of those, but what are some of the other ones?
So yeah, we touched on the ordering of the different flavors of neutrinos, the mass hierarchy. We've touched on CP violation, matter, antimatter asymmetry. We briefly mentioned Majorana, and that experiment and the successors, the scaled-up versions, are exploring a very rare nuclear decay called neutrinoless double beta decay. It's sort of ironic because you're studying neutrinos by looking for a process that does not give off any neutrinos. The neutrinoless double beta decay projects hope to inform us on whether the neutrino may be its own antiparticle and the implications that might trickle down in terms of theories of why the neutrino is so light. We have quarks, and we have electrons, and then we have neutrinos. And if they couple to the Higgs boson, you may remember a splash that the Higgs boson made several years ago about how the Higgs boson gives mass to elementary particles. The neutrino was such an outlier that we scratch our heads and wonder how it can receive mass in the same way. And there are other theories that if the neutrino is its own antiparticle, there may be what we see now is the light neutrino balanced out with a heavy neutrino that was that was generated early on in the birth of the universe after the Big Bang. So the seesaw mechanism, and that would also inform some of the grand unification theories of all the forces coming together. So there's studying this one process might lead us to hints or more than hints on some of these big theories that are out there as well.
Okay, Jaret, we got in a late question. This is a two-parter.
Oh.
So the first part of this is, how will all of this impact people's lives in the future? Speculation encouraged. And this is from Eric. I hope I say this right. Hoppy or
Oh,
Hopp?
yeah, Eric Hoppy. Hi, Eric.
And secondly, why does a beer and burger at Louis taste so darn good after a day underground? So let's take the first part.
Let's take the more serious one. Why does this matter? Different people will answer that different ways. I think if you ask scientists, they are all about the increasing knowledge, understanding how the universe works. But there are a whole bunch of other reasons that this is important. If you're a taxpayer, having people in your state, in your country, trained, highly qualified, trained personnel on the latest technology. You can build research programs, you can build up universities, attract faculty with a lab like SURF. Some of the sensor technologies are being pushed by some of these experiments. And so that's another reason there could be spin-offs from technologies developed from basic research that find their way into the commercial stream. And one example potentially would be, and this is something Eric's very, very familiar with, is electroformed copper. So we do electroformed copper as part of the Majorana demonstrator experiment. They needed to demonstrate techniques for building what are the world's purest, most sensitive experiments for looking for this rare neutrinos double beta decay project or a process. There may be some applications of electroformed copper in industry. I'm not sure. Eric would know that answer better than I do. But there are, so there's the sort of lofty increasing science knowledge, training, teaching, educating our students, to possibly spinning off technologies that will impact who knows how many sectors. And then why Louis Burger and beer tastes so good. Well, I think it's when people come here, they work really hard. And I know when Eric was setting up the electroforming lab over near the Ross shaft and at the Ross campus, those were some hard days. And I'm almost certain that that's why those burgers and beers tasted so good.
Okay, well, thank you so much. And if you could just stay there for a minute, Jaret, I'm going to step up and we've got a special gift for you.
Oh, my. Put my mask on, I guess.
So, you know, normally when we have guests, we have a beautiful photo that is depicts the Ross shaft, and it's a black and white photo, but you already have
I'm already enjoying it.
So we had to come up with something new for you, and guess what? You're going to be one of the first recipients of Surf Swag.
Very good.
So thank you so much. We appreciate it. That was a wonderful talk, and I know I learned a lot, and I'm sure everybody else did too. So thank you so much. And I'm gonna, if you could take your computer, I will close out the event tonight.
Let's go. I'll leave. Thanks.
Thank you so much. Well, I just want to say again, thank you to our Deep Talk sponsors and the Surf Communications team. I'm very fortunate to work with the Surf people, Matt, Adam, Aaron. They've just done a magnificent job putting this event together. I also want to give you a reminder to join us on Thursday, January 13th for a talk with the EGS CoLab group. And you may or may not know that's a geothermal energy group. They're going to be here in January, and we'll have more information coming up very soon on our website and social media channels. Finally, a recording of this talk will be shared on Facebook, Vimeo, and YouTube channels, SURF's YouTube channels. So feel free to share it with a friend who may have missed the live event. When you leave tonight, you will be given the option to take a survey about your deep talks experience. We'd love to hear from you. So please give us some feedback through this survey. Thank you for joining us and have a great night.